Alright, so the derivative in the tangent line problem. Okay, so what we want to do, and this is a great little thing, is we want to understand what the definition of the actual way to do this. Okay, alright, so real fast, calculus grew out of three major problems that European mathematicians were working on in the 17th century. The tangent line problem, the velocity and acceleration problem, the minimum and maximum problem, and the area problem. Okay, so the tangent line problem, okay, sets it up like this. So you have the tangent line problem is how do we approach to find the tangent line that is tangent to a curve at a certain function, let's say c. Okay, we can find the secant line so far, but we can't get really, we can get really close, we can kind of approach, that's where the limit comes from. Okay, so the slope between the 2 points is actually the difference quotient. Okay, so it's going to be the limit as delta x approaches 0 of f of c plus delta x minus f of c, which is just the difference in the y's, which is just like delta y, over delta x. That would equal the slope. So that's where the slope actually comes into play. Okay, so let's find the slope of the graph of f of x equals x squared plus 1 at the point -1, 2. Then find the equation. Okay, so we know we're approaching -1 and we're supposed to get 2 as an answer. Okay? Alright, so we plug everything in, we just set it up. So what we do is we take x squared and we plug it in to each part. Well, we actually take the x plus delta x and plug it into x squared. So this becomes delta x, or x plus delta x squared plus 1, and then the second part is just where we plug in x. So it just becomes minus x squared plus 1. Therefore, the slope at any point x comma f of x is given by m equals 2x. We'll get to that in a second. Okay, so we square this and we get x squared plus 2x delta x plus delta x squared plus 1 minus x squared plus minus 1. The 2x squares cancel out. The 1's and the -1 cancel out, so all I'm left with is 2 times delta x plus delta x squared. I factor out the delta x squared. Okay, because if you remember in finding limits analytically, we need to factor as much as possible because we don't want to end up with something, because if we let delta x actually get to 0 during substitution, then we've got an issue because we've got 0 on top and 0 on the bottom. Okay, so we factored out, the delta x's cancel out. And if you think of delta x not as a concept, but actually as a variable, this all makes sense. Okay, so we're left with 2x plus delta x. Now, the limit of delta x, limit of this function as delta x approaches 0, well, this is just going to turn into 0, and so we're just left with 2x. So what is the slope at the point -1 comma 2? Well, the slope is -2, and the equation of the tangent line is we just plug in these points into the formula, and there's our point slope form. Okay? This limit is used to define the slope of a tangent line. It is also used to define one of the two fundamental operations of calculus, which is differentiation. Because here, I want you to look at this. The formula, the actual function was x squared plus 1. The slope of the line that is right here, the slope of the line at that point is actually -2, or is 2x. Okay, if you notice there's an x squared and a 2x, that isn't just a coincidence. Okay, so the definition of a derivative of a function is just basically the difference quotient. Okay, all right, and we're going to call this this f apostrophe x as f prime of x. Okay, some other notations are here, and I'll bring it down a little bit. dy over dx, y prime, d over dx of f of x, and d sub x of y. So there's a lot of different types of formulas, okay? Alright, so find f prime of x for f of x equals square root of x, and use the result to find the slope of the graph of f at the points 1, 1, and 4, 2, and what happens at 0, 0. Okay, so we take our function, okay, we take our difference quotient, and we plug in everything. So we're plugging in x plus delta x into the square root, and we're plugging in just x, and we get this. Okay, now if you remember when we were doing limits analytically, we had to do the conjugate, so we multiply top and bottom. Okay, and so we end up getting x plus delta x minus x on top. Okay, and if you notice, if I write those out, these are going to cancel out to 1 or 0. The reds are going to cancel out there. Now on the bottom, I have a delta x in front, so I'm not going to distribute it. I'm going to leave it right there. And that delta x and that delta x are going to cancel out to 1. Okay? And if I scroll down a little bit and look at it, okay, I'm going to look as the limit approaches of delta x approaching 0. So this becomes 0. Okay? These just stay as square root of x, so I get 1 over 2 of the square root of x. Okay? So that's kind of cool. Now I'm going to remind you something. Your rational exponents, this is x to the 1/2. Do you think that's a coincidence that there's a 1/2 that appears with my actual derivative? I think not. Okay, so my slope is 1 over 2 times the square root of x. Therefore, at the point 1, 1, the slope is 1/2. Okay, so I plug in 1 and I get 1 and I'm there. And the point at 4, 2, the slope is 1/4. What happens at the point 0, 0? The slope was being defined since it produces a division by 0. Okay, so that's pretty simple, pretty easy. Okay, now finding the derivative with respect to t for the function y equals 2 over t. Okay, so once again, we take t plus, now instead of x, we're going to be dealing with delta t. So we take t plus delta t and plug it into it under here, and that's where we get this part. And right here we plug in t, and we just subtract the 2, so we need a common denominator, obviously. Okay? And then we multiply by 1 over t, delta t. Okay? So these two will cancel out to 0. All I'm left with is negative 2 delta t, and the delta t's will cancel out. So I'm left with negative 2 on top, and I'm left with t times t plus delta t. Well, delta t is approaching 0, so this is like t times t plus 0. So that's t times t, which is t squared. And there we go. And so that's 2. So that's really interesting. I went from positive to negative. I haven't done that before. Okay? Now the alternate form of the derivative is given as f of c minus, or f of x minus f of c over x minus c. So that's another way to write it too. Oops. Okay. Derivatives from the left and the right, you just be basically doing the same type of thing. Example of a point that is not differentiable. Okay, so this one is continuous at x equals 2, but let's look at this one-sided limits. Okay, so we actually plug it in. Okay, so we're going to take x minus 2 and plug it in. Okay, so we get x, absolute value of x minus 2 minus 0, because that's what happens when you plug in 2, you get 0. Okay, and so this cancels out to, or this simplifies to negative 1. Okay, this one simplifies to 1. Oh, when you plug in 2 from the negative side. So as we plug in 2 from the negative side, or from the left side, negative side. From the left side, like 1.9, 1.9, this is going to be 0.1. This becomes negative, so no matter what, these two will divide and we'll get a negative 1. Okay, whereas right here, as I approach from the right-hand side, let's say 2.1. Okay, I plug in 2.1, I get 0.1 on top, and on the bottom I go 2.1 minus 2, I get 0.1. Okay, so that's 1, so this would actually not be differentiable at that point. Okay, the one-side limits are not equal. There go. X is not differentiable, and this little 3 dots means ergo, or therefore, x is not differentiable at x equals 2. Also, the graph of f does not have a tangent line at the point 2, 0, which makes sense because it's pretty much a straight line. So at any point you're trying to pick a point to work with, it's going to be funky looking. Okay, now function is not differentiable at a point which a graph has a sharp turn or a vertical tangent line. Okay, differentiability can also be destroyed by discontinuity. Y is the greatest integer of x. And tangent line, y equals x to the 1/3, which is the cube root of x, or y equals the absolute value of x. Those ones are the ones you just can't mess with. You just, bleh. They're just rough right there. Okay. All right, but that's the derivative in the tangent line problem, and I'll show you a little bit more tricks next time on how to do derivatives. But remember, use your derivative function. If you don't have this problem memorized for the AP test, you're going to be having a world of hurt. So I'm going to write it out. Delta x as x approaches 0. Okay, and it's f of x minus delta x minus f of x over delta x. And remember, if you follow your rules for finding limits analytically, this problem becomes really easy to work with. Okay? All right, thank you guys, and have a great day.